Yeah. Okay. We're gonna start now. So hello everyone. Welcome to week 4. If you haven't already, please fill out the attendance form just so I know that you're here. But yeah, today there's not a lot going on assignments wise, but this is gonna be like a more in-depth talk about manufacturing and kind of like design processes and like workflows that you should think about when making your final project and just making things in general. So this is your final project. I talked about it a little bit last week. So basically, you're gonna get to create your own model from scratch. You're gonna use at least 5 design features, which should not be too hard. But I added that it must be designed with manufacturability in mind. So CAD is great because you can let your mind run wild, and you can make all sorts of crazy things. But when it comes to making it in real life, sometimes we forget that things have to exist in real life. And if you don't do it right, then your CAD will just become a mess when you try to make it in person. So yeah, we're gonna go into like talking about how to keep these things in mind when making your designs so it's very easy to manufacture later. But yeah, here are some examples of some people's finished projects. Some of them are more manufacturable than others, but overall, these are some very cool ones, some of my favorites. If you're having trouble finding ideas, you can look at this list. You can literally make anything you want, which is really cool. But yeah. So yeah, today we're going to be teaching you how to design with manufacturing in mind. So there's many kinds of manufacturing processes. Today we're just going to go into the 2 big ones. The first one is subtractive manufacturing. So it's when you take like a big block or just some form of material and then you cut away at it to make your final product, right? So you see on the left here, it just starts at this big square, and then this tool comes in and cuts a bunch of stuff away, and then now it has like this round part and this weird edge on the side. So that's one way to manufacture things. There's lots of tools associated with it. So there's drilling, milling, turning, routing, grinding. These processes are a lot of kind of the things that you think about when you think about making stuff, right? You're gonna cut a piece of wood and you're gonna build a house or something like that, or you're gonna drill holes and make stuff cool. But there are other things. So there's additive manufacturing, right? So additive manufacturing is when you start with nothing and then you build up something until it makes your product, right? So you see on the left, it just kind of starts as this weird flat plate, but you see it like grows over time into that piece that you wanted. So there's 2 examples of additive manufacturing. There's injection molding, which many of you are familiar with. It's very common with like mass manufactured parts. So like Legos are injection molded, and probably a bunch of other things are injection molded somewhere in this room. I'm gonna guess like these chairs are injection molded or something. But also there's 3D printing, and I like 3D printing a lot because it's very cheap relative to other manufacturing techniques, and it doesn't require like any extra tooling at all. So when you look at subtractive manufacturing, you have to worry about jigs and fixtures to make sure you hold down your parts very well. But with 3D printing, you just press go, and then your part just like appears like many hours later. But yeah, it's really cool, and it's really accessible to us students. So that's why we like to talk about these things. And we're going to be doing a demo for you today. So here are some applications of 3D printing. The industry has like grown significantly over the past few decades. So you see like a lot of people think of 3D printing as like a rapid prototyping thing, but it has grown into something a lot more. So like Adidas makes 3D printed shoes for some of them, which is pretty cool. But you can do all these things, right? You know, they 3D print stuff and it goes in cars. I know Porsche 3D prints their pistons for one of their high performance sports cars, which is really cool. And you know, there's other bigger things happening like 3D printing houses and stuff like that. So it's a really cool up and coming industry, and we get to tap into that too. So there's many types of 3D printing. So these are more like industrial grade level printing, especially SLS. But they all basically do the same thing, right? You basically have a bunch of material and then you either melt it or you cure it in some way to make a part grow, right? It just kind of grows the part instead of cutting away. So SLS uses powder. SLA uses resin, so it's kind of like epoxy. They shine a light and it grows. It's pretty cool. But by far the most common one that we see around us is FDM or FFF 3D printing. And basically what it is it's how I like to describe it is it's like a hot glue gun, but with a robot attached to it, right? But instead of glue, you're using plastic. So what it has is it has a heater. So you see the heater has a nozzle on the end with a certain diameter. And then the filament, which is just a big spool of plastic, will just be pushed through it and your robot will move the nozzle around and then it will make your part for you. It's pretty cool. I really like them. I have 3 of them. Well, actually, I have 5 of them. Aaron has 2 of them. And there's a bunch of them around campus. So there's some things to understand about 3D printing, just because there's so many settings associated with it. We're going to be teaching you how to slice a part later, but these are just some different parameters that you can change in the settings. So the first one is layer height. Layer height is a really big thing because it can significantly increase or decrease your print time. Because basically for a 3D printer like this, it just has a single nozzle and then it basically draws a bunch of 2D profiles of your part and then it moves up every time it finishes a layer, right? So what a slicer does in the name, it will slice your part many times to create 2D profiles to make your part, right? So you can change the resolution and you can make it look nice or you can make it print fast, right? So you see there's like drawbacks to all of these. Yeah, what's up?
There's no kind of like intelligent software that like be like really like can have a small layer height on the outer edges, but like a big one in like the middle where nobody's seeing it. Does that not exist?
Not really. You can have variable layer height, if that's what you're talking about, but mostly it's on like a per layer basis thing. But yeah, so you see on the top left, it has a layer height of 0.8 millimeters. So you can see like on this presentation, even if you're far away from the screen, you can see the different layer lines, right? So that means it like just extrudes a lot of plastic and then just makes your part faster, if that makes sense. If you've ever like changed the settings on your 2D printer, this is basically like DPI, but in 3D, if that makes sense. But yeah, so that's cool. Perimeters are also very important. It really like determines how strong your print is going to be, but it also changes how fast you print it. So a lot of these settings you'll notice it's a drawback of how strong or how nice you want your print to be and how fast you want it. Because you know single nozzle and it just moves around. So you see on the left there's only 2 perimeters. You can see 2 little lines. So that part may not be the strongest, but if you increase the number of perimeters, the wall thickness on the outside will be stronger and it will make it less susceptible to damage depending on your situation. All of these settings can be tuned for the specific part you're making, which is really nice because you can optimize it and save on speed or optimize for strength. Just this is all like up to the person manufacturing. The other two important things to note is infill. So in most 3D printed parts are actually hollow. If you didn't know that, that this saves on material and printing time because a lot of the inner material is not super necessary, like structurally, right? The main like benefits that you get structurally is like number of perimeters because that adds a lot of rigidity to a certain extent. So you see on the left, there's like 10% infill, so you can see it's very hollow. And then as it progresses to 50%, you can see how the mesh on the inside gets denser. So again, if you want higher infill, it will become a stronger part, but it'll take more time and you'll be using more material. Supports are also very important because 3D printers, although it says 3D, it can't just like make things in midair, right? So it's susceptible to gravity. So sometimes you'll need things uh, like sacrificial material to hold up parts of your print. So you see here on the left, it has like this like cylinder that comes out of the part. You need support material or else that part is going to droop when you're manufacturing it. That's just kind of how it goes with 3D printing. So yeah, here's another example of supports. You see it's very horizontal and, printing in midair isn't great. So adding supports is nice. One thing to note is, adding supports is more material and it's waste material. So you're not going to be able to use it again. Generally, when you're 3D printing, you want to try to avoid designing parts that need supports unless you really have to. But I'll go into that, like how to optimize that later in the lecture. Yeah,
so like here you could just like lay them down and then you wouldn't need the support material.
Yeah, you could do that too. Print orientation is important. An SLS printer doesn't need supports because it uses the powder as supports. Yeah, but I'm mostly talking about FDM 3D printing today. But yeah, so this is going to be your only assignment for today. You're going to have homework, but yeah, we're going to teach you how to slice a part, and then we're going to run the demo, and then I'm going to talk to you a little bit more about 3D printing and designing for 3D printing. So if you go into resources on the Discord, you can see there's a download link to Prusa Slicer. So if you click on it, it'll take you to Prusa's website and it gives you like a bunch of different download links. Click the one in the middle. So the one that says drivers and apps 2.6.1. Yeah, it should work for Windows or Mac. And yeah, just run the installer, like unpackage all the stuff. And then we'll start making that slicing stuff. Yeah. What's up? On the rubric it says 1.5 millimeter speed, but that's not actually options. 4.5. Did I write 1.5 instead? It is probably 0.15. Well, it says 0.5 on the 0.15 on the slides, but not the.
Which one do you choose? Like these options?
Oh, what? You should probably, if you just click on download for Windows, it just should start right here. Oh, click mark 4. Okay, yeah. It doesn't matter, they're all the same. So just click the middle. Yeah. The slicer is the same for all the printers. I will probably make it after week 5, but I would prefer you get it in by the end. Yeah, probably. Yeah. Just whatever's selected, just like click it. You don't need to add any additional things. But yeah, so as these installers are running, it should be pretty quick. I'll just let you know that there are a multitude of different slicing softwares out there. Some of you already have them. So, there's like Simplify 3D or Ultimaker Cura. There's a bunch of them, but they all essentially do the same thing. I'm just teaching you Prusa Slicer because we're doing the demo on a Prusa machine. But you can use a sliced file from another slicer and use it on the machine or on a different machine. So yeah, download it, and then we're going to be making this benchy right here. So additionally, there's also a benchy file in the resources folder. Should be called 3dbenchy.3mf. Please download that because that's going to be your assignment as well. Is anyone having trouble downloading Prusa Slicer? It should be more straightforward than Fusion. So
Once you download and open everything on this page, what do you do?
yes, I will walk you guys through that.
Did you download the bench?
Alright, so now that everyone has it downloaded, when you open Prusa Slicer, it'll open like a welcome wizard. If you accidentally closed it, I think you can go under. Yeah.
Do we restart us at the move?
Yeah. No. Okay. So you'll be greeted with this like welcome screen, and then you're gonna get to select which printer. So basically, Prusa Slicer is like an open source software. So there's a bunch of printers that this slicer is compatible with. So we want to make sure we're choosing the right one. So over here, it says Prusa FFF after the welcome button, or you can press next. And it'll show you like Prusa's host of printers, right? So for this assignment, I'm just going to ask you to use the original Prusa Mini and Mini Plus at the 0.4 millimeter nozzle, right? So you're just going to select that check mark, and then you're going to press finish. Is that clear to everyone? Oh yeah, so if you accidentally closed it, you can go over this on this printer drop down. I have like a bunch because I have a bunch of different printers, but at the bottom it says add or remove printers. And if you click on it, yeah, add physical printer. Yeah, so it looks like this, but if you scroll down, then the mini's there. Oh, are the pictures not like appearing? That's strange. Yeah.
This is a much more intuitive system. No, no, as in the fact that like okay, to move like linearly, you have to like double with like hold the mouse. To rotate, you should be able to just use the left side. I like it. Better.
The spool holder's in my car, but I don't know if you want to walk that far. Okay. Oh, let's go. Okay. So is everyone at this point here? Is there anyone not at this point? Okay, cool. So so once you get here, this is Prusa Slicer. This is just kind of their interface. So in this really big area that says Original Prusa Mini, this is your virtual build plate, right? So all 3D printers have like a limited volume that you can print in, and when you're preparing your file to print, you're going to be using this virtual build plate to make sure everything fits correctly, right? So on the right here, there's a couple settings that you can change. So over here is the layer height or the resolution like I was talking about earlier. So if we want to set these specific settings, it should be 0.15 millimeter speed. So if we click on this, there's this drop down over here. Here's the 0.15 millimeter speed. I'm going to select that. The filament type, it doesn't really matter because we're not actually printing this. This is just for your reference. But there's a bunch of different filaments. I use PETG. It's a pretty common filament. There's a bunch of others like PLA and ABS. I could talk all day about different filaments, but I won't go into it. Over here, there's like supports on or off. So you see like earlier in the slides over here, this little blue, dark blue area, those are all supports, right? So for this file, I'm just going to select everywhere. Generally for this thing, you don't use supports, but this is purely for demonstration purposes. Infill over here, you can change the percentage. So I set it to 20% here. So you go in the drop down, you change it to 20%. And that's like, those are like the three, or like, yeah, the three most basic and most important settings. Change this. So now that we have these set, I'm just going to insert the part just so we can start to visualize what's going on. So I'm going to hit Control I, or you can do like file, like import, or you can even drag the file in. But I'm going to find this 3D Benchy file. I'm going to import it, and then now we have like this little green boat on the build plate, right? So you can see like in relation to the build plate, it's going to fit, right? It's not too big, which is good. And over here, you can see like just some general specs, right? So it's like 60 millimeters wide, 31 millimeters in the other direction, and 48 millimeters tall, right? So this is just some nice information for us, but we're going to want to change some more settings, right? So over here, we want to change the perimeters to 3, right? So you can see on the right side, the number of perimeters aren't there, but over here on the top left, you can change things under printer settings. And over here, you can see there are more options. I think it defaults to like the simple option, but when you get into 3D printing more, you can like unlock a bunch of different settings that you can change for like optimizing stuff. But for now, we're just gonna keep it simple, and then we're gonna change the number of perimeters. So over here, I'm gonna click on layers and perimeters. You can see there's a bunch of different options here. So perimeters is right here under vertical shells. And it says 3. So in this case, I want 3 perimeters, right? I'm going to leave everything else the same. Supports are on. So all these are on, right? So if you're following along, you should get 100% on this assignment, basically. If you press slice now, so if you're in print settings, you can go to platter. You can see your build plate again. You press slice now, and then your computer will generate the movement commands for your printer. So if you didn't know, 3D printers are actually not very smart, right? The smart comes from the software attached to like the G code. So G code is basically like a super long list of commands for your printer to follow, and your printer will do exactly what it says on the G code. So if you have bad G code, you can like make your printer do things that it can't physically do, right? So like over the summer, I was just messing around with it, and like I would manually write G code, and you can like tell the printer to move like 3 miles in like one direction, right? And it'll try to do it, but like it can't move that far. But basically, your computer will generate G code, and it should not break. So you can see here, if I zoom in, like before, this was kind of smooth. You can see it's smooth. But if we look over here, you can start to see the layer lines if we zoom in a lot, right? Does everyone see that? Yeah. So in this, you can also view like the different layers like on a layer by layer basis. So you can kind of see this process here. So the printer starts with like nothing, right? It's empty, and then it basically draws a bunch of lines. This arrow is the nozzle, and it will just draw a 2D profile of your model, right? In this case, this 2D profile is 0.15 millimeters tall. Once it finishes with this layer, it will move up by 1, and then it will just go off from there. So every time the layer finishes, it moves up and it makes a new layer. That's basically how 3D printing works. And that's why it looks like your part just grows. Does that make sense? I think it's kind of cool. Oh, I just kind of like drag the arrows. Yeah, there's like an arrow on the bottom. You can like drag it. Okay, yeah, so that's the nice thing about this software is that if you have a print like a part that's too big, it just won't let you slice it, right? So I don't know. I'm gonna let's just say I scale this up like super big, right? Like it doesn't fit on the build plate anymore, so it turns blue. And you can actually see like this highlighted, like the lighter blue area is the part where like it does fit, but you can see like this is obviously too big, and like it throws an error and it like doesn't allow me to slice it. So you don't have to worry about that. Oh yeah. So for this assignment, if you have all the settings right, basically just submit it once this loads. Submit a screenshot like this and make sure all this sliced info is in the screenshot, right? So this will help me gauge if you did it right, because if you like, let's say didn't put the right amount of infill, then like the used filament, like the weight of the part will be lighter and it should take like less time, right? So it should be about 2 hours and 58 minutes. If it's like slightly different, then that's probably just a rounding error and don't worry about it. Yeah, if you take a screenshot like this, you should get 100%. Let's go. Oh, something to note, if you ever change any of the settings after you slice it, you have to slice it again. Like, it says export right now, but if I change it, then yeah, I think like yes. So yeah, so the slicer is used as for part. It goes from STL to so if you I can actually open up the G code. It's kind of interesting. This is like kind of extra enrichment stuff. Where is it? Okay, yeah, so this is the G code file, and this is the file that your printer is going to read. So as you can tell, it's not really readable for like normal people, unless you're like weird like me, right? But like all of these, each line is a command for the printer to follow, right? So G1 is like a movement command, and you see it has like specific coordinates for the printer to follow, right? And you can see from like this scroll bar, this thing is like thousands of lines long, right? And each movement is like very small and precise, if that makes sense. Yeah.
You know how long a step is? Like each line tells it to move like a little bit. How long is each step?
Well, it depends on the movement command, right? So this is telling it to move like in between these points, it's like I don't know, half a millimeter in one direction, like fractions of millimeters on this end. And then E is for extruder, so it's like how much plastic you want to push, right? So yeah, it's very precise.
Yeah, it only deals with one flat plane at a time.
Exactly, yeah. So the 0.15 is basically your resolution vertically, right? So like how I was saying, how the layer height is like the DPI, but in 3D. So you see this is 0.1 and this is 0.3. Like 0.15 would be like somewhere in between here, if that makes sense. Oh, it says modified because you like change the number of like perimeters and stuff. Because the default is like 2 and you just changed it. But yeah. So yeah, this is cool. If you're weird like me, you'll learn how to read it and then you're gonna go crazy. But maybe don't do that. But does that make sense to everyone? Do you have any like general questions about printing? There will be time to do that because we can do that during the demo or something. Let me see. I don't know if I can turn my camera on for the video. Let's see. Start virtual camera. Can I like
Because it's a display capture, it's not using the.
Yeah. Let me see. No. That sucks. Okay.
Maybe, there's a plus sign in sources. Try adding like your.
Facts. Let's see.
What do you,
Video capture device. Wow, you can see me. This is fun. Okay. So we're gonna run the demo now. So if you all want to get up from your seats and huddle by the printer, then we can do that. Okay. I'm just gonna like point it towards the printer. So because you guys came to class today, I'll take so these were all made on this printer like in 2 hours. It's pretty cool. the box. Yeah. So this little thing here is my handy Prusa Mini. I like it a lot. It is one of my first printers I've had, and it's really reliable, and yeah, I really like it. Um, so basically, you all know how to slice something now. Um, to make it run on the printer, you'll use some storage device like a USB. This one takes USB. Some printers can do it wirelessly or on SD cards or whatever, right? But basically, you'll turn on the printer. It's already on. There's like this nice screen here. But I just put this USB in, and this printer is like pretty smart, so it basically will do it for me. So it like read the USB and then saw like the latest file, and it just pops it up. So over here you can see the little bench that we did earlier, and then I'm just gonna press print, and then it's gonna go. But first it has to heat up. So now we just stand here and wait. But yeah, it's just kind of like general construction of the printer. This is like what people call a bed slinger. So this printer, like the build plate itself, is on a moving axis, along with the nozzle on its own axis, and then the nozzle goes up and down. Generally, these are considered to be like cheaper to manufacture, which is why they're very popular. And yeah, they're pretty nice. Boom. Okay, so each axis has a motor. So these are stepper motors. They can like precisely control the distance at which the extruder or the bed runs on. It's all running on belts, except for this, which is on this big lead screw. Yeah, there's an extruder on the back, which is basically like two wheels that pushes this filament through the nozzle. And that's basically how a printer works. Do you have any like questions about 3D printing? I don't know how familiar you are with it. I mean, it's becoming more mainstream. Oh yes, this is something cool. This printer is 3D printed. So Prusa is like an open source company, so they publish all their files, and you can make your own 3D printer with a 3D printer. So I bought this from Prusa, and Prusa has like this factory of printers to make more printers, which is cool. So a lot of these black pieces are all 3D printed, but there's some metal components. It's part of something called like RepRap, which is like this early 3D printer philosophy that printers can replicate themselves, right? So they like say like we have like a parent, and it makes like a child printer, and then like that child can make more printers. So it's kind of cool. Yeah, so that's why you see this is 3D printed. There's a bunch of other printers on the market that are moving away from that philosophy. But yeah, I don't know. I've had this printer for almost four, yeah, for almost 5 years now. That's crazy. And it's been dead reliable. It's good. This is like low key a marketing for Prusa, but yeah. I don't know. A lot of you might be familiar with like Ender 3s. You've probably heard of them. It's a very like cheap 3D printer, and it's one of my first printers. Yeah, it was his first printer. They're cool. They're cheap, and they'll make stuff, but they'll start to like break down and degrade over time. But again, I've had this for 5 years, and it's still going strong. Yes, I'm totally not. I'm not sponsored, but that would be cool if I was.
Yeah, but you'll find that most supercomputers are technically projects of their own. So if you want to work on projects instead of working on your printer, it's probably best to spend the money and get a preset.
Yeah.
Because I had an Ender 3 that was like $200. I spent just as much time trying to fix the printer as I was printing things and making things with that printer itself.
Yeah. And
That's why we really
this
like that.
mini is about double. So this was about what, 400, 450 bucks.
Just about.
Yeah, but I can press go, and like this was in my dorm last year, right? So I'd press go, I'd like go to like physics lecture or something, and I'd come back and like it didn't break down, so that's good. Um, yeah.
When it starts pulling from, isn't this orientation going to be a problem, or can the thing spin?
Oh yeah, so I forgot my spool holder today, but it's like this like some rollers on the side, and it will just like roll that way. If it becomes a problem, then I will hold it. Oh yeah, so it's heated up. It will run through its homing sequence. So this printer has auto bed leveling. So you see this like little sensor on the side. It can sense the metal on the build plate, and it will allow you to like know, or it allows the printer to know how far the nozzle is from the build plate. If that makes sense. Um, the first layer is very important. So having auto bed leveling is super nice. Um, just because if any of you have used like an Ender 3, there's like knobs on the bottom of the build plate to like level it, and it can get tedious and annoying, but this will do it for you. Yeah. Most printers these days like are starting to come with auto bed leveling as standard, so that's nice. Um, but I would say like 2 3 years ago that was not standard, and you would spend a lot of time being sad and using a piece of paper to level the bed.
You guys ever tune a guitar? It was almost like tuning a guitar, but like every time you tune one of the strings, one of the other strings would go out of tune. So you just kind of like juggle how to get it perfectly level. It's very annoying. This is much more efficient.
And then every time you like print and you want to print again, then you have to level the bed again, and then you get sad. Um, let's see other features on this. This has a filament sensor, so it can like detect when it runs out of plastic, which is nice. Um, that's also something that's kind of becoming standard. Um, yeah, yay, it's starting. So you see, it will kind of go through this purge tower where it'll extrude a little bit of filament, and I'm running a alpha firmware, so it's actually really fast, and I hope it doesn't mess up. The estimated time is 1 hour, but we're not just gonna sit here for an hour.
Should we give it more?
Well, I sliced this before. Um, um, I made it slightly less dense, but I mostly bumped up the print speed because this printer is capable of doing that now, which is nice. Um, I guess this is like kind of being a bit technical, but input shaper is kind of like an up and coming thing for a lot of printers. And it basically is resonance compensation, right? So when a printer moves around, it will like vibrate a little bit, um, and depending on the mass of like all the parts, it will resonate at a certain frequency, um, and input shaping can compensate for that. So it allows you to print faster without any like visual defects. If that makes sense. It's like kind of complex, but it's really cool. Um, but the main thing is it allows you to print fast, and that's nice because people always complain about printers taking forever, which they do. Yeah. So you see, like the bottom is like solid infill, right? So it moves around in like a zigzag pattern, and it makes the whole thing like flat. Yeah. If you don't have any other questions, then I'll just like continue talking and lecturing. I'll pull up the PowerPoint. But if you won't have questions about printers, then you can do it now or after class. Okay, I guess you don't. But yeah, me and Aaron have been printing for a long time, so if you have questions, feel free to ask us. Because yeah, we love printers.
You guys work in shops like this?
We don't, but we I have printers at home, and I run a small printing business.
I work in the machine shop. Not the machine maker, sorry, the 3D print lab. And the machine shop. It's 3D print lab.
Okay, yeah.
What printers?
We have like 4 Ultimakers with the really fancy resin printers, and then we've got a ton of Einstarts, Impulses, and I'm blanking on the last one, but that's what all of them. I'm so good at remembering what slicing software we use for each, but not the actual name of this printer.
They have a lot of bed spinners.
We have a lot. It's like
the blue ones, right? Like
Yeah.
the fake
we
Prusas.
print. Well, the reason we're being running is we print our own gears. For them.
Years.
Gears, like extruder gears.
Mhm.
Mm.
That move the entire thing. They're huge.
Oh yeah. Okay. Yeah, I know what you're talking about. Those are kind of cool.
Remember, because I was doing senior design stuff, not for myself, for the seniors, not a senior. And there was this print that kept failing. It was like a 2-day print, and it just kept failing. And it turned out that one of the gears was stripped entirely.
That would do it.
It was totally new.
Would get nothing to do. It never worked. Like,
Yeah.
the last thing you had, you get a piece of paper for it.
Oh,
Yeah.
It's cheap on Amazon, and you still can get it.
Yeah, the first printer I got for free because my friend thought it was a piece of trash and he decided to give it to me. So I got a piece of trash and I almost lit my house on fire.
Oh no.
Because so you know how printers heat up the plastic, right? So there's this ceramic heater cartridge. So these two red wires go into this thing that is basically just like a big resistor, and it gets really hot and then it melts the plastic, but that fell out of the hot end. And it didn't have thermal runaway protection. So there's like a thermistor on the metal block that will like record, or it can analyze like the temperature of the hot end, which is like the metal block, but the heater cartridge fell out. So the like the hot end temperature went down, so it put more current, like it pumped more electricity into the cartridge. Yeah, because it's like, oh no, it's getting cold, we need to heat it up. But it wasn't heating up because it had fallen out. So I woke up the next morning and there's like this red hot piece of ceramic is on the build plate, and it was like, yeah, it almost like caught my house on fire. So yeah, that's why you buy nice printers, so you don't have to worry about your house catching on fire.
My club uses the SLS, the Synchro printer, the 3D printer process stuff.
Oh,
It's like it's just so easy to load and like coding.
yeah,
I'm on the team that like prints and then prints the machine after it.
yeah,
The powder is much
yeah, yeah. I don't know. Oh, another nice thing about this printer is that the build plate is made of a flexible steel. So once the print finishes, you can take it off and like bend it, and the part will just fall off, which is really convenient. A lot of older printers would use like glass as the print bed, which is good because it's really flat, but the print would like stick to the glass, and you'd have to like scrape it off, and sometimes you like take chunks out of the glass, and then you'd get sad. Yeah. Or you can be my brother and step on my build plate, and then it broke. But, yeah. I started 3D modeling in high school, so I was on a robotics team, and we made robots, and that's how I started 3D modeling.
My problem is I know a lot about printers and not a lot about printmaking stuff.
Yeah. So I started on the manufacturing side, and then I moved to design. So I guess I will be lecturing in a bit, but the point of this lecture is for me to pass on my manufacturing experience to you, so you don't have to print things and be like, oh no, it doesn't work, and then you will be less sad. Because, yeah. Well, I hope you're happy, but yeah. Yeah, because there's a lot of like minute details when it comes to modeling that you don't think of right away until you start making things. So the hope is I'll tell you now, and then you'll think about it when you're making your final project, and then I'll get the final project, and then I'll be happy because it will print really nicely. Because, okay, I'll get into this later, but like you are limited to like certain thicknesses, right? And like bridging and stuff, I'll get into that later. But someone like modeled the Golden Gate Bridge in a previous semester, and like everything was super thin, and it was basically unprintable. Like at the end, we did get it to print, and when we took it off the build plate, it snapped in half. So not super ideal. So I want all of you to have cool models that don't break because it makes my life easier, and then you'll have something that'll last a long time. But yeah, I guess I'll get into that now because there's lots of design considerations.
Yay.
Okay, click hide this. All right. Okay, so yeah, so this is a great segue into 3D printing limitations. So every manufacturing process will have its limitations. I'm just going to be talking about 3D printing today because that's what's most relevant for this class and most likely most relevant for you, at least at the time, at your time in Purdue, you might all 3D print something at some point. And these are some things to consider. So the first thing that you want to consider is overhangs, right? So again, this 3D printer is extruding a plastic through a really tiny nozzle, and it isn't, or it's subject to the forces of gravity, right? So if you try to print something at a really aggressive angle, then the printer will have a hard time doing that. So you see, like on the top left, the angle is not very sharp, right? It's just kind of up, and it's, not very aggressive. I like just saying aggressive, but you can use whatever word you want. The middle one is like, it's kind of getting there. It's pretty tough. You see, it's a 45-degree angle. And then on the far end, it's probably like 30 degrees. And then that's when you want to start to worry, or you might start thinking about supports, right? So generally, when you're modeling, 45 degrees is a really good, like, safe number when you want to make something angled, right? So how do I explain this? Yeah, 45 degrees. If you have anything more than that, it'll start to droop. I don't know if I have a good example of it. I guess here. This is like a 90-degree angle, right? This pipe piece on the bottom, and that is technically an overhang. But because it's at 90 degrees, I would suggest supports, right? Just because you can't print in midair. So supports are useful in this case, but it is also useful for other angles. So let's say if you have like a 30-degree angle, supports will be your friend. But because you're the ones designing your parts, you can choose that angle. So when you're modeling, it's good to keep in mind the print orientation and like the angles, right? So yeah. Does that make sense? Do overhangs make sense to you guys? I don't know if I was just saying too many words. Okay, cool. So this is another example of an overhang. It's something that I didn't really think of when I first started making stuff, but technically, if you have a vertical circle, the top of the circle is going to be like a really aggressive angle, and it's going to be an overhang. So you see on the gray part on the top left, like the top of the circle is drooping, and that's because it's technically an overhang. So a good way to combat this is by modeling like a teardrop shape instead of a circle for all your vertical holes. So you see on the right side, they basically what you basically do is you draw like a perpendicular triangle on the top of your circle, and then you just cut everything out, just so it's a nice teardrop. So the top is going to be tangent to the circles, or both lines are going to be tangent to the circles, and they meet at a perpendicular angle. And that basically makes it 45 degrees, if that makes sense.
What if for some reason you need it to be like a perfect circle? Then what do you do?
If you need the hole to be a perfect circle, then
Supports inside, like the hole?
yeah, you could use supports. That works too. Like honestly, like I've found that most of the time you actually don't need a perfect circle. So like I've made like stuff for like bolt holes and threaded inserts. I just made the teardrop shape and it worked just like a normal hole.
Really be a perfect circle, you should design it to put it in line. So the circle is facing.
Yeah, that's the other way to do it. This is just for vertical holes though. Horizontal holes are fine because it's just a hole. Yeah. Yeah, so this is something to keep in mind. These are all just like overhang stuff, but overhangs will sneak into places that you don't expect. Bridging is also a limitation of 3D printers. So you'll see that when it makes long bridges, you'll see it starts to droop, right? So the plastic is drooping just because gravity will pull the filament down before it gets to cool. And if you have really long bridges, then your prints won't turn out as nice. Again, you can use supports in this case, right? The supports will like make sure that your bridges don't droop. But as a designer, when you're designing for 3D printed parts, you want to try to avoid using supports as much as you can, because that means that you don't need to do any post-processing, right? You can just take off the part and use it. And it reduces the materials, right? So all the support material is wasted filament, where you could have put it to a part that you're making, if that makes sense.
So for the example on the left, you could fix that just by like laying it down, and then you wouldn't have that problem anymore. But like the example on the right, it's like,
yeah,
how do you deal with it? You have to use a support.
You would have to use a support, or you would have to tune in your print settings like extremely well, but that depends on your printer. But these are just like examples. Like the one on the right is actually like a bridging like torture test, right? So it's just like allows you to see how far your printer can bridge, and then using like that data, you can like design things with that in mind. But a lot of this comes down to either print orientation or design, right? So if you want your thing to be a certain way, you can design it in the right orientation. But if your model doesn't allow for that, then you have to either design it out or add supports. Yeah. Thermal expansion is another thing. So as you can see, this 3D printer is like $400, right? So $400 to like a student might seem like a lot, but if you compare it to other manufacturing processes, it's very cheap, right? So like a milling machine will like run you like thousands of dollars, but with those thousands of dollars, you get a really nice piece of heavy machinery that is extremely precise, right? You can make things down to like thousands of inches, right? Like fractions of hairs. But 3D printers aren't that precise yet, right? So a lot of the problems that you'll get when 3D printing comes from thermal expansion, because when you heat something up, it's gonna expand, right? So when the nozzle heats up the plastic, once it starts to cool, the plastic will shrink. So you see on the top right, the plastic shrunk to the point where it peeled itself off the plate, right? And that's not ideal. So part of this can be mitigated by, tuning your printer correctly, but it's also like a design thing. Elephant's foot is something that is caused when a printer's nozzle is too low at the start. And a lot of the times people do that they add elephant's foot to make the printer or make the plastic stick, right? Because you don't want the part to fall off while it's printing. But you'll have elephant's foot. So you see that like little circle photo, you can see the first two layers are like squished outwards, right? So that like reduces the like dimensional accuracy of your parts. And what you can do to mitigate this is you can add a chamfer on the bottom of all your parts, right? So if you add like a 45-degree cut on the bottom, then even with elephant's foot, it'll still be like kind of straight, if that makes sense. Generally, printers have a tolerance of like 0.2 to like 0.3 millimeters. So it's not really meant for extremely precise things. But yeah. Here's a good example of like thermal expansion. So this is a previous project from I think 2 semesters ago. This person designed like this Lego guy, right? And in CAD, all of the pieces meshed perfectly, right? But the thing is, thermal expansion exists in real life, so the parts aren't exactly what they are in CAD, right? It's slightly bigger, and when they went to assemble the Lego man, or the torso didn't go all the way on the legs, right? So sometimes this is like a trial and error thing, because then from this data you can be like, oh, like I'll just like change the diameter of it slightly, and then when you print it out, it's the right size. Yeah. I would prefer that it's one piece, but if you really want to do more than one piece, that's fine. Just keep in mind that I only have a couple printers and there's a lot of you, so yeah. I think someone like submitted like a whole chess set to me one time, and I'm like, no, I can't make all of them, even though it was really cool. The model was great, but yeah, I'd prefer it's one part. Yeah.
What is the size limitation has to fit on this?
Okay, I'll get back to you on size limitations. I think in previous semesters it was like 20 millimeters cubed, but I forget because most of the time people forget about that and they just submit like really.
Is that
I don't I don't remember. Maybe it's like 5 centimeters cubed. Yeah, I don't remember. I would just say like just keep it reasonable. Like don't send me something that's like extremely big, because that takes a long time to print and that means you're taking more time from other people's final projects. Yeah. Oh yeah, your homework, there's gonna be like a quiz on this stuff. So I hope you're paying attention. It's like not gonna be that hard. I didn't make the quiz yet, but I'll send it out soon. Um, yeah, that's about it. I guess I forgot to add this. The one thing to consider when you're modeling is layer orientation. So you can see on like this layer on the layer height photo, you can see all the layers of the print lines, and those are actually like points of failure. So if you ever like had a print on in like a high stress environment, you can see like, and if the print breaks, it often breaks on the layer lines. So the layer lines and like layer adhesion is very important when it comes to 3D printing. And technically speaking, if you print more layers, you're making more points of failure. So if you want a stronger part, sometimes it's actually good to print at taller layer heights. Yeah, it's kind of interesting. Um, but yeah, I don't know. If you want to look at like the little 3D models I gave you all, you can see on like the vertical axis or like along the width of the P, you can see the layers. Like if your P was like super long and you like tried to bend it, it would snap on the layer line. And that's important when designing things for high stress, where you can, when you design your part, you can design it to be printed in an orientation where the layer lines aren't there, if that makes sense. Like if you wanted something to be like really long and it was like going to be bending like this way, then you would like print it on its side. So all the layer lines wouldn't be in that direction. It would just, you would just be pulling the plastic instead of pulling the layers. If that makes sense. Yeah, so filaments, there's a bunch of different filaments out there. So by far the most common filament that you'll see people printing with right now is PLA. And it's basically like this recycled material made from like corn. And it's really easy to print. Like the prints can come out really nice with minimal tuning. But it has like a really low melting point, and mechanically it's not as strong as other filaments. So I use PETG, which is like slightly stronger, but it's still relatively like reasonable to print with. ABS used to be like really popular, but it's really difficult to print with. So ABS is like a very common injection molded plastic. So I don't know if you've all had like Nerf blasters, but all of those are made of ABS. So it has a really high melting point. So if you leave it in the car, like you don't have to worry about it melting. For PLA, like under some circumstances, they can kind of warp if they get too warm. So that's something to keep in mind. PLA is very easy to print. So it has a low melting point, and it just makes it very flexible to print with. So this Prusa has like a heated bed, and it heats up the build surface so the part doesn't cool down too fast. So if the part does cool down too fast, you can see from like the thermal expansion slide. Where is it? You can see like if the part cools down too quickly on the top right, it'll like fold up. And that's like that basically doesn't happen with PLA, or it's very hard to do that with PLA. Like you can print PLA with like without a heated bed. That's how like easy it is to print. If that makes sense. Yeah.
A lot of the stronger materials require you to have like a very, very hot end. It needs to print at PETG prints at like 230 degrees Celsius. Stronger filaments will need to be like 300 plus. And that's
Yeah.
something most printers cannot do. So I think the strongest you can get out of a print like this is polycarbonate.
Yeah. So they're like polycarbonate PETG blends. So they'll like mix polycarbonate in with PETG to get you a stronger filament, but they're generally more difficult to print with. So if you didn't know, polycarbonate is what they use to make bulletproof glass. So it's like really strong. But with strength usually comes difficulty in printing. There's other materials like nylon, which are also like printable, but those are also higher temperature and more difficult to print. Yeah, maybe don't stand. Oh, yeah, technically you're like not supposed to like leave a printer like unattended, but you also don't want to breathe in the fumes. So like you want a very well ventilated area when you want to print something, because
It's less of an issue. There's been research suggesting that it is fine for humans.
yeah, PTG is odorless,
Yes,
but
PETG is odorless.
that means you don't know if it's good or bad for you.
But with any FDM printer, as it prints, it's heating up plastic. It's gonna throw off tiny, tiny microscopic like specks of plastic, and they are technically harmless, but if you want to be safe, it's probably best to not sit and leave with a printer for like 24 hours. Like this is fine.
Yeah, you're probably printing with ABS. Yeah, ABS is pretty strong, but it can be kind of brittle. Yeah. Again, it's basically a hot glue gun. Yeah. I don't know. Yeah, I mean, we're basically done. Feel free to hang around, work on your final projects, or ask me questions about 3D printing. Yeah, or you can watch the printer finish. I need to make the quiz, so I'll post it soon, TM.